Later this year, the universe may have a special treat in store for everyone who is fascinated by our cosmos. Reports state that a terrifying supernova will be visible in the sky for all to observe. While our cosmos is littered with the remains of exploded stars, witnessing such an event with the naked eye is an extremely rare occurrence that happens only once every few decades. Let's talk about what causes these massive stellar explosions and what you can expect to see in the sky when it finally happens. A supernova is a name given to the cataclysmic explosion of a massive star at the end of its life. It can emit more energy in a few seconds than our sun will radiate in its lifetime of billions of years. The sky above us is strewn with alluringly beautiful remnants of ancient supernovae. That is, stars that lived out their lives and then died in these violent explosions. In a galaxy like our Milky Way, consisting of some 200 billion stars, there should be a supernova as often as every 50 years. Yet supernovae, visible to the eye alone, are exceedingly rare. You might, or might not, witness one in your lifetime. What we do see are supernova remnants, expanding clouds in space where stars used to be. There are many examples, both inside and outside our galaxy. The most famous supernova remnant visible from the northern hemisphere is called the Crab Nebula. It's located in the direction of the constellation Taurus the Bull. The Chinese recorded witnessing the supernova in the year 1054 CE, although it had occurred 6,523 years earlier because this star was that many light years away. They called it a guest star and wrote that it was visible in daylight for a full 3 weeks, finally fading entirely from view about 3 months later. Later, the Crab Nebula became famous for hosting the first known pulsar, discovered in 1967 by Jocelyn Bell Burnell. The Crab pulsar, as it is known, is a neutron star, the remnant of the supernova that created the Crab Nebula. Like cosmic lighthouses, pulsars give off beams of radio waves as they spin. The beams from the Crab pulsar happen to be aimed our way. We know that supernovae are star explosions. We see examples of their aftermath in the space around us. We know that, as the star explodes outward, it also implodes, forming an exceedingly dense neutron star that might or might not appear to us on Earth as a pulsar. But what exactly is a supernova, and what makes it explode? Astronomers are slowly peeling away the layers of mystery surrounding these exploding stars. Their sheer unpredictability is exciting. Each supernova teaches us something new. Astronomers have learned much about supernovae in just the last 50 years. A bright supernova in our Milky Way galaxy is now, statistically, long overdue. Let us hope it happens in our lifetimes, but preferably not too close. A supernova is a more final and more powerful explosion than a nova, which is the temporary flaring up of a dwarf star in a binary system. In the nova scenario, the dwarf star collects matter from its companion star. The excess mass causes the dwarf star to flare up suddenly, now and then, to many times its normal brightness. Then it fades, over time, to its original brightness, before the next flare-up. A supernova, on the other hand, is a much bigger and intrinsically much brighter event, where the outer layers of a star are blown explosively into space. A star that goes supernova does not return to its previous brightness and may disappear completely, leaving an expanding supernova remnant behind. Both novae and supernovae were once called stellanovae, a term coined by the famous Danish astronomer Tycho Brahe in 1572. That is because both novae and supernovae can cause a new star to appear in our sky where none was seen before. Both flare up suddenly and, in the case of supernovae, unexpectedly, before slowly fading away entirely over weeks or months. Now we know that a supernova is not a new star, but quite the opposite, an existing one that has reached the end of its life. And we know that novae, the less powerful flare-ups, mark the location of a star system that might flare up again. Supernovae can have different causes, but all involve the sudden detonation of a star. Astronomers currently recognize two main types of supernovae, Type 1 and Type 2, according to a way of classifying them devised by German-American astronomer Rudolf Minkowski and Swiss astronomer Fritz Zwicky. Hence, the classification system is known as the Minkowski-Zwicky system. The classification is based on the spectra of the supernovae, that is, on their light, when it is split into its component colors. Type 1 supernovae lack the presence of hydrogen in their spectra, while Type 2 supernovae display it. Type 1 is further divided up into 3 subtypes, 1A, 1B, and 1C, also based on their spectra. But maybe more exciting is the difference between the types as determined by the cause of the explosion, and here, a bit confusingly, types 2, 1B, and 1C are actually the same type of explosion, while type 1A is a completely different creature. Type 2 are the most common supernovae that occur in the universe, and they are also what people normally think of when they think of a supernova, a star exploding due to old age. Type 2 supernovae occur when a large star runs out of fuel, which brings it into a rapid collapse and explosion. Such a star is between 8 and 40 times heavier than our Sun. They are often referred to as core collapse supernovae because that's exactly what happens. The star's core suddenly, in just a few seconds, collapses in on itself. But let's set the scene for that cataclysmic event. For billions of years during this star's lifetime, nuclear fusion, the process by which hydrogen is converted into helium in the star's interior, in the process liberating huge amounts of energy, thus enabling the star to shine, had been fighting a battle with gravity. We're not talking here about the gravitational attraction of one object toward another, but about the star's self-gravity. In stars, the outward-pushing radiation from fusion reactions in the star's core is continually being countered by an inexorable inward-pushing force of gravity. It's a duel of forces in which neither can be the victor. As long as the nuclear fusion at the core of the star is maintained, the star stays in balance. But stars are born with a finite amount of hydrogen fuel. After billions of years, changes begin to take place as hydrogen is depleted. Once the core of the star completely runs out of hydrogen, nuclear fusion in the core ceases. The star has nothing left to burn. At that point, the star is no longer able to maintain its outward push against inward pulling gravity. The star slowly starts to shrink. This shrinking has the effect of bringing more hydrogen from locations further out in the star into the region previously occupied by the core. This is sufficient hydrogen for the nuclear fusion to resume in a shell around the star's inner core. However, there is something called the mirror principle, to do with the conservation of gravitational and thermal energy, which states, very simply, that if the core of the star contracts, its outer layers must expand. So the star starts to swell, expanding massively from its original size. As it does so, its outer layers cool, being further from the shell effusing hydrogen at the core. Once the temperature cools sufficiently, convection, rather than radiation, becomes the dominant way the outer layers of the star are heated, and the star stops expanding. The star has become a swollen, cooler, and hence reddened version of its former self. It is now a red giant star. When our Sun becomes a red giant, in about 5 billion years, it will expand to consume and destroy Mercury, Venus, and possibly Earth too. This means that the Sun's diameter will increase some 115 times. It will also brighten by perhaps 3,000 times. But, dramatic as its brightness increase may be, we are not at the supernova stage yet, and reaching the red giant phase is not the end of the story. As the star's core continues to shrink, temperatures inside it rise to even higher levels than before, reaching a staggering 100 million degrees Celsius. At this extreme temperature, and if the star is massive enough, it can start fusing the next element in the periodic table, that is helium, into carbon, and nuclear fusion starts up once again in its core. Temperatures rise even further until the helium is used up, leaving a core consisting of carbon and oxygen. The burning of its helium, however, is not a rapid process. A star 8 times the mass of the Sun will probably have enough helium to last 100 million years. However, during all that time, the temperature of the core slowly increases, and when it reaches 500 million degrees, it's hot enough for the next element to start fusing. Carbon nuclei fuse, producing sodium, neon, and magnesium. All of these are burned in turn by the star. The core continues to heat up, reaching 2 billion degrees. As the temperature climbs, first silicon is formed, followed by sulfur, argon, calcium, chromium, manganese, and nickel. Each is burned in successive shells as the core continues to shrink until the star resembles an onion. Each element created in this stellar nucleosynthesis is progressively heavier, consisting of larger numbers of protons, neutrons, and electrons, until, eventually, one element is produced that cannot be burned: iron. At this point, the temperature at the star's core may reach 3.5 billion degrees Celsius, and its onion layers consist of a dense iron core surrounded by shells of silicon and sulfur, oxygen, carbon, helium, and an outer shell of hydrogen. It's incredible to realize that, to reach this late stage in its life, the star might have been in its red giant phase for 1 billion years. As iron cannot be burned, not even at these temperatures, the star truly has reached the end of the road. The effect of the core's final collapse, which takes perhaps just a second or so, is to send a shockwave right to the center, which then rebounds and propagates outward through the outer layers of the star, completely blowing it apart. Copious amounts of energy are released. Hence, the brilliant event we know as a supernova explosion can be seen across the universe. A few years ago, a study predicted that in 2022, 2 stars would merge, leading to a colossal explosion in the sky. This was the first of its kind prediction of a red nova that would be visible even to the naked eye. Humanity has recorded 8 naked eye supernovas in the past 2,000 years, the latest being Supernova 1987A in the Large Magellanic Cloud, one of the Milky Way's neighboring galaxies. The light from the supernova reached our planet on February 23, 1987, and it was the first supernova that modern astronomers were able to study in great detail. The red novae have a characteristic red tint that sets them apart from other novae. Unfortunately, the prediction that we will be able to observe this event with the naked eye this year seems to be false. The story began in 2013 when Professor Larry Molnar from Calvin College and his team began analyzing a pair of tightly bound stars known as KIC 983-2227, located in the constellation Cygnus, about 1,800 light-years away from us. They observed strange blips in the brightness of the stars, hinting that the 2 stars were periodically blotting each other out. Upon looking at the data, astronomers suggested that the 2 stars were on a collision course that would happen at some point in 2022, causing a red nova in the sky. However, various teams began working on validating and checking the accuracy of the nova prediction at the same time, and this is when unwelcome news arrived. In 2018, while analyzing the archival data, a group from San Diego State University spotted a typographical error in the archived orbit of the stars. The time of an observed eclipse was mistranscribed by precisely 12 hours in the publication, and it was because of this unintentional blunder that Molnar's calculations regarding the timing of future eclipses were incorrect. When this typo was corrected, it no longer predicted the stars of this binary system to merge and produce a rare red nova. Even though this is disappointing news for astronomers the world over, it's only a matter of time before a visible stellar explosion illuminates our skies once more. If you enjoyed this video, you may also be interested in this other one, which looks at the Hubble Space Telescope and how it recently discovered a hidden galaxy. Do you think humans will get technologically advanced enough to stop the sun from dying? Please share your thoughts in the comments section below.